Welcome back to ECE 320A. We're still in Unit 10, and now we're getting into the fun part. Now we're actually going to put all of these pieces together. We'll break it down again into each of the steps, and then we will sketch those individual pieces for these Bode plots, and then put all of those pieces together, add the magnitudes up as we go from small frequencies to large frequencies, from left to right in our diagram, and we'll also combine the angles, add those up, all of the terms, however they contribute as we move from left to right, and you have to keep track of when things are sloping, when they are just flat, etc. And we'll do that now in this video for this first transfer function, which I hope you're starting to sort of see what's going on by just looking at this transfer function itself. We have a gain of 10,000. We have a 0 at minus 0.1, we have a pole at the origin, and we have a second pole at minus 100. That's in pole 0 form, and we know to sketch the Bode plot we have to change that up. And after we do the hand sketch, we'll quickly show how you can verify that in MATLAB. So we actually do have the answers in the back of the book if you go to MATLAB and start implementing or expressing the information of this transfer function in the proper way in MATLAB. And so you have a way to check your sketch, or you have a way to check what you're putting into MATLAB or how you're using MATLAB. Here's just the reminder. We're doing Bode plots. That says then that we have two different plots, a magnitude plot and a phase plot, both on this semi-log paper, where we now have frequency as our independent variable, and it's actually log of omega. And we're doing all of these assuming that we have minimum phase transfer functions, or all of the poles and all of our zeros are in the left half of the complex plane. Our strategy hasn't changed. We simply identify the individual pieces that we have, and we may not have all of these pieces depending on the transfer function. And then what we want to do in this video is focus on how we do step 2 of this strategy, which is add up all of the terms together. So let's now do the Bode plot sketch. Here is our Bode, or our transfer function in pole 0 form. We factor out the constants from the different linear and quadratic terms. Here we don't have a quadratic, but now I've shown how we can then cancel essentially some of these zeros off of 10,000. First by multiplying 10,000 or taking 10% of that, and we're down to 1,000, and then we divide that 1,000 by 100, and now we're left with 10. So in our time constant form, we have our gain of 10, and that will be easy to sketch in a Bode plot. We have one linear zero factor, or one real zero, at a frequency of 0.1 radians per second, and that's convenient. That's just 10 to the minus 1. We have a pole at the origin, and we have a pole at 100. And here I've tried to identify these individual terms, color code them. The first constant is green. The pole at the origin is black. The zero is blue. And the fourth term of the different individual pieces is our pole at 100, or with a frequency of 100, and that's in this purple color. Hopefully I can keep track of those colors, and as I'm sketching the individual pieces, we'll use those specific colors to try to make it clear which piece goes with what, and the final total Bode plot will try to be in red. So that's the objective. And sometimes as I'm doing this, I like to get my mind thinking about what I'm going to be sketching. And one way to do that is to quickly sort of provide myself with some notes via a word description. So let me just illustrate what I mean by that. First, we have our constant term, and that constant term k was actually 10. And we can immediately see that that's positive, so we know what the angle is. But let's first talk about the magnitude. The magnitude we compute in dB, so we take 20 log of that particular value of k, which is 10, and log of 10 base 10 is 1. So now we know this constant piece is providing 20 dB of gain for all frequencies. Phase, it's positive, k is positive, so our phase of that positive number is 0 degrees for all frequencies. That won't be hard to sketch. The pole at the origin is the next piece that I'm writing a word description for. And the poles at the origin, or the zeros at the origin, those just produce slopes. They don't break. So here we have, excuse me, a magnitude that's always sloping. It's a pole that's downstairs, so our slope is negative, or as we're going from left to right, we're falling with respect to that slope. We only have one pole at the origin, and that then it's a single pole. That gives us this 20 dB per decade, and it's negative. We need to figure out where do we plot that sloping line on our Bode plot, and a convenient frequency is omega equal to 1. At omega equal to 1, J1 has a magnitude of 1, 20 log of 1 is 0, so we're at 0 dB right at that frequency of omega equal to 1. We're bigger than that in magnitude as we go to the left. Omega is smaller, omega of 0.1, 0.01, etc., or 10 to the minus 1, 10 to the minus 2. And as we increase in frequency, the slope is negative, so now we'll be less than 0 dB. We'll be minus 20 dB when we're at omega equal to 10. We'll be at minus 40 dB when we're at omega equal to 10. Or I'm sorry, at omega equal to 100. The phase, now this pole at the origin, there's no constant piece, and so the phase is always 90 degrees, and since it's a pole, it's minus 90 degrees, and that's true for all omega. That's easy to draw. You just get your ruler out and you just draw the straight line, flat horizontal line at minus 90 degrees, and in this case I'll try to encode that as a black line. We have our single zero, real zero. It's at minus 0.1 location-wise in the complex S-plane. If I had to draw the poles and zeros, or the pole zero diagram, I would have a zero sitting at minus 0.2, or an open circle. In the Bode plot, now our independent axis is log of omega. We're 0 dB. Now it does have a break. It's 0 dB until we reach the break frequency. Again, this is the way that we're performing our approximations. And then, since it's upstairs, it's a 0. It slopes up at plus 20 dB per decade, and that's all there is to it. The phase is a little more involved because now we have to start and stop the slope change. And the phase is only changing or sloping within a 2-decade expanse, or a 2-decade interval, and that 2-decade interval is centered upon the break frequency, and in this case that break is at omega equal to 0.1. A decade before that break, we're going to just say we'll approximate everything below that as 0 degrees. A decade beyond, or a decade above the break and beyond, we'll approximate everything as 90 degrees. We're upstairs, it's a plus 90 degrees, and we just connect those two points that are 2 decades apart. From 0.01 to 1, we draw a straight line in the phase to connect 0 degrees at 0.01 to 90 degrees at 1 radian, which is a factor of 10 beyond 0.1. Finally, again, we're doing the word description. We have our single pole. Our second pole, we had a pole at the origin. Now this one has a break to it, and it's going to break at omega equal to 100, since it has a pole at minus 100 radians per second. We're flat then at 0 dB until we reach omega equal to 100. Then it's a pole that's going down. It's a single pole, so it goes down at minus 20 dB per decade. What am I doing? Let me hope that I've not been doing all of that wrong up until this point, but this is now 20 dB per decade. Well, maybe I should check that. So there's 20 dB per decade. Okay, it looks like I was just off on that particular point, so please erase that or correct that. So it's sloping down at minus 20 dB per decade. Again, we have our 3 frequencies to draw the phase. It's a pole, so we're going down. We start at 0. We end up at minus 90 since it's just a single pole. We begin that sloping a decade before the break, which is at 10 radians per second, and we stop the sloping at a decade beyond, which is at 1,000. So let's now see if we can put all of these pieces together. Here is the semi-log grid or diagram. I've already actually drawn the constant and I've labeled it as 1. It was a 20 dB line, horizontal line for all frequencies, and I've tried to then show this green line going from left to right over all frequencies at 20 dB. The second piece in this sketch is our pole at the origin, and I've already given myself some hints as to, or some ways of sketching this. I know that that goes through 0 dB at 1. It then goes down 20 dB in a decade interval of frequency, and it goes down another 20 dB. And so at 100, we will be down at minus 40 dB. If we go all the way out to 1,000, that particular factor, just that pole at the origin, will be contributing minus 60 dB of gain. If we move to lower frequencies, remember, this pole at the origin does not break. It always is sloping. Then it was going down, and it just continues to go down, but it does not break. It continues to go up, which at 0.1, it's going to be at 20 dB. At 0.01, it's going to be at 40 dB. And that's now what we have for the individual component of the pole at the origin, its magnitude. It now contributes this sloping line. This is now individual term 2. Individual term 3 was our single 0. That's 0 dB until we reach the break, which is 0.1 or 10 to the minus 1. And that now is going to be flat until we reach here, and then it'll be 20 dB bigger a decade beyond the break, and another 20, so it's sloping at plus 20 dB per decade after it breaks. The pole at the origin is minus 20 dB per decade. And finally, we have our single pole at 100. Let's now see if I can get the color correct, and it's 0 dB until we reach its frequency or break value, which is 100, and then a decade beyond, or at 1,000, it'll be at minus 20. A decade beyond that, it's going to be at minus 40. It's now going to be contributing its slope of minus 20 dB per decade. We now have all of the individual pieces. This is piece number 4. And we can now put all of those pieces together. And the way to do that is to move back to low frequency and start to see what is actually moving or participating among all of the pieces. If we go back, and far enough back in this case is 10 to the minus 3, we don't have anything contributed by terms 3 and 4. They're both at 0, but we do have 20 dB from the first component, and we have 60 dB from the second component. We add those up, 20 and 60, that now makes 80. So we'll have a magnitude of 80 at 10 to the minus 3. At 10 to the minus 2, nothing else has happened other than we're sloping down the constant. So we have 20 from the constant, 40 from the slope. So we're at 60 dB, and we're sloping down. And we can then connect those dots. But let's go one more decade before we start having something changing in our slope. So at 0.1 or 10 to the minus 1, we have 20 dB from the first term or the constant. We have 20 dB from the pole at the origin, and we have nothing yet from the third and fourth term. So we're still sloping down, and we have now reached 40 dB in our total magnitude plot. At this point, though, we have to start paying attention. We're sloping down at minus 20 dB, and now we're sloping up at plus 20 dB. Those slopes actually cancel, and so we are now going to be going flat. And if we go flat and actually compute what happens, we had 20 dB due to the constant. We have 0 dB due to the pole at the origin, and we have 20 dB due to the 0 at 0.1. 20 and 20 gives us 40, so that is consistent. We look over here, and we have 40, plus 40, and plus 20. That's plus 60, but we have to take 20 away from that, so we're still at 40 dB. So we're still flat. We haven't seen anything additional introduced with a slope until we get to beyond 100. And at 100, now we have two poles sloping down, each at minus 20 dB, and one 0 sloping up. So now we have a net slope of minus 20 dB per decade, so that beyond 100, we should be sloping down at minus 20 dB per decade for high frequencies. And we started at 40, we're 20 dB down. A decade beyond that, we're 20 dB down, and I'm not sure I'm going to get this in the right spot, but somewhere in there we're 20 dB down, and we just keep sloping. So now let's connect the dots. We don't go flat, we're always sloping for low frequencies. That just keeps sloping. So we're minus 20 dB per decade because of the pole at the origin. Then we have more things kicking in, and we go flat until we reach our second pole, which is individual piece 4, and then that, in combination with the pole at the origin, causes a net slope of 20 dB per decade beyond omega equal to 100. And this is now the total of your magnitude plot, and that's what you should see, something like that, when you start to sketch it or see it sketched via MATLAB. So we're now, the pole at the origin gives us this negative slope for all frequencies omega. Then the 0 causes us to stay flat in magnitude at 40 dB, so that's now an amplification of 100 in absolute sense, and not until we reach 100 in frequency do we start rolling off again in our frequency behavior for the magnitude plot. That's now the magnitude. Let's now look at the phase. The phase, we have the constant gave us 0 degrees for all frequencies. The pole at the origin gave us 90, minus 90 because it's a pole. So here is the contribution due to the pole at the origin. We then have the 0 that's breaking at 10 to the minus 1, but we know that we're going to transition over a 2-decade interval, and we transition from 0 degrees to 90 degrees. It's a 0, so it's going up. And then we simply connect those two extremes with a straight line. And this is now piece number 3. Piece number 4, let me go in and find the right color. Now that breaks at 100, but we transition it over a 2, we have slope of over 2 decades, and we're 0 until we get a decade before the 100, which is at 10, and we're at then minus 90 because it's a pole beyond that. So now that is going to be sloping, and this slope is minus 45 degrees per decade because we change by a total amount of minus 90 degrees after 2 decades. Likewise for the 0, that's now plus 45 degrees per decade. Let's see if we can put all of those pieces together. And we can sort of anticipate what's happening in totality. At low frequencies, the only phase contribution is due to the pole at the origin, which is giving us minus 90 degrees. And then we actually see some bump positively due to the 0 at 0.1. So now if we look at that particular influence, we will be at minus 45. When we add minus 90 and plus 45, we end up at minus 45. And then once we reach 1, all of the phase from the 0, we're assuming in our approximation, has been contributed. So it gives us 90 degrees. The pole at the origin gives us minus 90, and the constant gives us 0. So we're now at 0 degrees, and we don't have any contribution in phase until we reach our pole. And now we really effectively have just the pole, the second pole contributing. That now contributes, and it stops contributing a decade beyond. So here I should, it's a little, so here's our total curve in red, and it actually overlaps with our 4th individual term that kicked in at a decade before its break, but now that 4 is the individual piece of our second pole. And we could check this, we could sort of check what's happening. In fact, we had, what, 2 poles and 1 0. So at high frequencies, we have essentially 2 minus 1, 2 poles minus 1 0, or 1 pole in effect, and 1 pole produces minus 90 degrees. And at high frequencies, in fact, that's what our phase curve is saying, that we're at minus 90 degrees for phase. At low frequencies, the only thing acting is the constant and the pole at the origin. The pole at the origin gives us minus 90 degrees. The constant was positive, so that gave us 0. So we start off at minus 90. We start at minus 90, we transition, we go flat for a little bit, and then we transition back and end up at minus 90 degrees. We can actually check that in MATLAB, and I've created a script file that I call vid 10.9 for this particular, to be consistent with this video. We can enter our numerator, and this could be in pole 0 form. That's fine. We say 10,000 times, and now our expression for, let's say, s plus 0.1, in MATLAB, we now encode from the smallest, which is the constant, and we just keep building or expanding to the left. Here we had 0.1 for the coefficient of the constant, and we have 1 for the coefficient of the linear term, and that's now what we've multiplied 10,000 by. I apologize maybe for all of the words, but this is now our numerator, and we could enter that in however we wanted to enter it, but we would have to be consistent with how we enter the numerator and the denominator. In pole zero form, the denominator was s times s plus 100, which is s squared plus 100 s plus 0 times s to the 0. So we now have a 1 coefficient for s squared. We have 100 for our s to the 1 coefficient. We have 0 for our s to the 0 coefficient. That's our denominator. We could check those roots if we wanted to. It's not necessary, but if we wanted to find the roots of a polynomial, we just issue that command in MATLAB. That command is now the roots command. We can do that for both the numerator and denominator, and we can check our work. We can now use the built-in transfer function in MATLAB, TF, putting in the numerator for the first argument, denominator for the second argument, and now we have this transfer function object that we've called H1, and that does look consistent with what we wanted. Here's how difficult it is to create a Bode plot. Now we just enter the function Bode with the argument H1, and it will produce a sketch of the magnitude and phase. And I'm just saying give us some grid lines so that we can maybe infer what's happening. I've also issued a few more commands. We could ask for the zeros of a particular rational expression, and that will give us the zeros. We could ask for the pole, and that will give us the poles of that rational expression. And we could even do a DC gain. In this case, we had a pole at the origin, and if you go back to our magnitude plot, the magnitude at DC is infinite. It just keeps going up and up. So this is consistent in MATLAB. It says, oh, it's infinite if we ask for the DC gain of that transfer function object. And here is what MATLAB would produce, or did produce, for that particular transfer function, and hopefully you can see that that is consistent with what we sketched. Obviously there's a little bit more curve to it because we were doing straight line approximations, but the shape is there and it's consistent with our hand-drawn sketch of the Bode plot. Congratulations.